All right, thanks for joining, folks. We are just getting things set up here and looking forward to having a good discussion with you today about, um, you know, building spatial data products and spatial AI for energy. Just give us a few minutes. I think we're going to probably start after about 2 minutes after the hour. We got some poll questions for you, some things that we'd love your engagement on as we go through this, but looking forward to the conversation. Every time we do these, I always like remind myself that we need to have some background music. All right. We are now officially 2 minutes after the hour, so I think we're going to go ahead and get going. And Phil, I'll let you take it away.
All right, thanks a lot, Ben. Hi, everyone. Phil Derringer, Principal Product Manager here at Wherobots. Today, we're going to talk to you about how you can use Wherobots to monitor assets at a global scale. I'm joined today with Daniel Smith, Staff Solution Architect here at Wherobots, and he'll be walking through a demo with you as well. All right, let's get started. I'm going to start with some background on Wherobots and the use case we're going to talk about today, and then we'll jump into the demo. So first of all, one of the realities we're dealing with today is just simply the lack of spatial data talent. There are a limited number of us out there that have familiarity with making use and getting value out of spatial data types of processing needed to truly extract value and insight from this type of data. So out of 47 million overall software developers, there's only about 1.5 million spatial software developers. Another context here is that the compute that's out there is really just not cost effective when it comes time to make this spatial data useful. Spatial data engineering is truly cost prohibitive with most traditional platforms. You have legacy solutions that really just weren't built for the types of global scale that we're talking about with these Earth observation pipelines. They may be constrained to a single machine or can only scale vertically. And then you have emerging modern cloud engines, but they're really not focused on geospatial. So they've limited geospatial support, either in the types of data types they can support, the types of functions, or not supporting both a combination of raster and vector operations that you truly need for these types of workflows. And finally, there's a lot of promise with LMs and agents that they're going to just solve all this. They're just going to make it work for us, help people that aren't familiar with geospatial start working with geospatial. But for people who try this out, it's just really not there today. It's still not the case that the LLMs have the context that they need or the expertise they need to build efficient and cost-effective pipelines for truly working with this data at global scale. So that's where Wherobots comes in. We're building out the AI context engine for the physical world. We're trying to eliminate this talent gap and also bring the full range of capabilities that you need for geospatial operations in a modern cloud computing environment. So we started with WherobotsDB. So Wherobots was founded by the originators of Apache Sedona. We've taken that Apache Sedona engine and its ability to run very efficient spatial compute on vector operations and raster operations at scale, and we've made it even more efficient inside of our WherobotsDB engine within our cloud. And then end of last year, we introduced Rasterflow, which is a new capability we have to run planetary scale inference, helping you automate any type of Earth observation pipelines that you may want to deploy. And then recently, we've opened it up with our spatial AI coding assistant. So trying to make it easier for agents, LLMs, or developers working with these tools to make use of these capabilities within their workflows. So that takes the form of our VS Code extension, our MCP server, and we'll have more capabilities coming out in this area very shortly to allow you as developers or agents themselves working with this data, working with these processing pipelines to build out these applications. And this is all coordinated and organized in our Wherobots Cloud managed service, where you can work with the spatial data, work with the models that you want to run, iterate and develop notebooks that you then deploy as production jobs. And now some of our new visualization capabilities are all fully managed in a Wherobots Cloud environment, a secure environment that you can work on by yourself or collaborate with other members of your organization. And last but not least, in terms of the enterprise architecture, where Wherobots fits in, it's a lakehouse architecture. So we can plug into your existing data sources, whether those are existing legacy GIS systems or cloud native storage, where you might have all of your spatial data. And we provide a platform to allow you to discover that data, build and iterate on geospatial pipelines that process that data, then build automation to deploy those at scale in a production environment that you can use in an operational setting, and then serve up those results to produce results that you might serve up in applications like Esri, like QGIS, like Felt, for servicing real line of business applications that need access to the results, the insights, the geospatial layers that you're processing and producing in Wherobots. All right, that's a little background on Wherobots itself. Before we get into the specific use case, I just want to open up with a general poll question. So we want to know more about how you're using agents today to build your industry-specific analysis or industry-specific workflows. So open up the poll question. If you can fill that out, there are 4 options there. Are you just evaluating data? Are you building analysis? Are you going all the way to productionizing data pipelines? Or if there's something else you want to talk about, please add that directly in the chat. All right, we'll give people a few minutes to respond, a few seconds to respond to that.
Yeah, we're getting some responses already. Just should have a prompt up in front of you just to fill out the poll. Would love to hear your response. All right, go ahead in the poll. So we had a few folks that said you're building analysis for my needs and use, and a few more that said productionizing data pipelines for my use cases. So didn't get anything else. Nobody evaluating data that I have for analysis. That's interesting. So, all right.
All right, cool. Thanks, Ben. Let's talk today about the use case we're going to go into in a bit of detail. So specifically, how do we use technologies like Wherobots to, at global scale, to detect methane leaks? So if you're not familiar with the problem about methane leaks, we'll give you a quick intro here. It's a huge problem. It's the second biggest driver of global warming after CO2. So methane in general as a gas has 80 times the warming potential of CO2 if you look at our time horizon of 20 years. And it's usually just caused by everyday operations, vents, flares, small leaks, but truly in aggregate works out to be a global scale problem. And you see the figure here, it's over 200 billion cubic meters of gas produced every year just through leaking. And that adds up to about 2/3 of what EU, for instance, uses on an annual basis. So a huge problem here. And it's also to say, like, this is just lost product, right? So from a oil and gas production perspective, anything that's lost through this type of leak is product that can't be sold. And finding it and helping to mitigate these leaks can often pay for themselves. You see here an image. This is of the Aliso Canyon methane production facility in Southern California. Site of one of the second biggest leak actually ever detected in the United States near a residential area, caused significant problems for that area and that community. All right. Now there's regulation that's coming into play here, specifically driven by the EU, out on the forefront of this. So 2027, they have a deadline that requires operators to prove that they're continuously monitoring every site that they have for leaks. And in 2027, what kicks in, this is existing regulation, but what kicks in 2027 is that it doesn't just apply to any production in the EU, but also to anyone importing energy to the EU. Now, the US also has regulations in this area. They are a bit softer, but because they would be exporters to the EU, this also applies to the US. And you see the timeline, how it goes beyond 2027. So beyond 2027, you actually have to start reporting the intensity of methane, and 2030 meet specific targets in this area. So how do people do this today? Well, typically, it's a bit challenging to do this truly at global scale. They're using a variety of different manual processes that don't always fit together or give them the complete coverage they need to provide that truly global coverage. So it might be a combination of sort of ad hoc ground crews going out with handheld infrared cameras to survey specific sites. They may be doing costly occasional flyovers. They may have sensors deployed at certain sites, but that might be sparse and not fully covering all the assets. And then there's always the promise of satellite imagery and using satellite imagery to detect these flares. And we're going to talk more about that specifically today. But generally, because of the historical tools to work with satellite imagery data, that can be very siloed. It's typically a specific team, or maybe don't even have those skills within your organization to build out those pipelines. So using that data can often be siloed and not integrated with the rest of the capabilities you might already be trying to use. So yeah, today we're going to talk more about how easy it would be within Wherobots to automate monitoring at scale and use the satellite capabilities to monitor your natural gas assets. So we're going to jump into a demo, but just as a prelude, we're going to talk about the specific raster capabilities we have within Raster in WherobotsDB that make some of this processing possible and efficient at global scale. So within WherobotsDB, you can work with raster operations natively in Spark SQL, use data frames to process this type of data. So we have built in support for what we call an OutDB raster. So you can efficiently work with the raster without pulling all of the raster information into memory. You're only selectively pulling the tiles, the specific pixels that you need to process into memory when they're needed for specific compute. And that allows you to run more efficient pipelines at this global scale. So that includes a built-in STAC reader. You can just point it to a STAC catalog and start ingesting that as an OutDB raster. Again, mostly the metadata that you're pulling in, and then setting the data frame up so that you can do efficient processing when you actually want to do a calculation. Any tile processing is all done in a distributed fashion using the power of Spark as a distributed compute engine. And that allows you to process, whether it's COGS, GeoTIFFs, NetCDF. We're adding support for ZAR here shortly. You'll be able to work with that in this data frame context. And then we have the built-in functions, so a set of core raster operations to then process those raster data sets, whether that's raster algebra, combining bands of raster data and computing specific indices and using band math, or doing pixel-wise calculations. And then the building blocks you need to resample that raster data to different resolutions, do reprojection to different CRSs, or any other reclassification and value remapping you might need to do. And last but not least, because we're a complete engine providing both raster and vector capability, you can use those together. So zonal statistics, for instance, I want to calculate the mean or the sum or average distribution of these pixel values over a specific geometry. That's a straightforward distributed operation in WherobotsDB. Or clipping, masking, applying geometries to clip and mask rasters. All that is built in as well. And you have a single language using Spark SQL or Spatial SQL capabilities to work with those vector and tabular data sets. All right, with that intro, I'm going to turn it over to Daniel, who's going to walk through a demo of how you can use these capabilities for monitoring methane and CNG production.
Awesome. Thank you so much.
All right.
Go ahead and
stop sharing.
Share my screen. Thank you very much, Phil. Real quick, my name is Daniel Smith. As Phil said, I'm one of the senior solutions architects here at Wherobots. I've been doing geospatial for about 20 or 25 years. So I'm going to quickly kind of show the Wherobots platform. I'm going to show a notebook that we've generated to kind of do two things. The first thing that it does is flare detection, and then it will look for flare dropouts and walk through a basic like methane detection workflow. And so the first part really is that constant monitoring of the flares. When that flare detection or when that flare has gone out, we enter into a second workflow. And then we're going to use our MCP to take this an analytical notebook and convert it into a job using the MCP server, our internal skills that are available through the MCP server. And one of the frontier models in this case, we'll be using Claude from Anthropic. So real quick, Wherobots, as we mentioned, is a hosted distributed cloud processing platform. The main interface kind of interacting with the platform is through our console here. You're given the ability to start and run your notebooks directly through here. This will create kind of a Jupyter, an interactive Jupyter experience that's hosted for you. So if you don't have Jupyter servers, or if you don't have a development environment that you prefer, we support this and host this for you. We have our data hub that contains all of our open data available here. You can add all of your own catalogs, and so this can either be within our managed storage, or this can be a Unity catalog from Databricks. We support Glue catalogs from Amazon, and a host of other data collections are on their way. Again, we support storage integrations from S3. We have managed storage, so if you guys don't have your own buckets or your data sharing policies don't allow those to be added, you can still leverage the managed storage that we have here. So I'm a big fan of VS Code, and so we actually have a VS Code extension. So rather than using the hosted environment, I'm going to switch over to VS Code, and we can kind of walk through the notebook here. Now, I'm not an SME in this area, but I have done a lot of research in the past, and so the process that we're going to work through here really leverages the MCP server when I was generating this, and so. The process loosely is taking a set of flare locations, using those with the MCP server and Wherobots to generate this notebook that'll do a couple of things. The first thing that it does is search and find all of the associated Sentinel-2 imagery within a time window. In this case, we're actually searching through an entire year of imagery to find all of the cloud-free data to start to do some of the thermal anomaly detection. With that generated via the MCP running in Wherobots, at the very end, we're actually going to live sample converting this into a job either with Airflow or using the Python SDK that we have built. So this is essentially we start with accessing our data, and so we consume all of your basic standard geospatial format. So we can ingest all of your shape files, all of your GeoJSON, all of your GeoParquet. We have an Esri feature service reader. So if you guys are getting this data from like the Living Atlas or from another source that's hosted from the Esri platform, we can consume all of those to kind of set the stage for all of our analysis areas. In this case, I've taken all of the areas and we've generated this rectangular buffer to make sure that, we're accounting for the distribution of like these individual sites. So it gets a little bit larger than the individual point data than we were loaded, or that we were given. This is the search part of this. It's a rather large code block, but it's really doing a lot of work in here. Not only are we filtering based on the cloud cover, so we're looking for all of the images that are less than 10% cloud coverage. We're applying our date as well, so we're looking for the entire year of 2025, and we're accessing and promoting all of our individual bands that we need for this analysis. So this would be using the near infrared, the SWIR 16, and the SWIR 21 band from the Sentinel-2 platform. Searching for all of these sites for the entire year happens in a little less than 7 seconds. So about 6 seconds, we've combed through the entire catalog, the entire STAC catalog for the entire year, and collected all of this imagery here. Now that we have individual bands, one of the things that you have to do is take all of these individual bands and stack them together. If you guys have used this information before, you'll remember that SWIR 16 and SWIR 22 are both 20-meter bands. In order to stack them up appropriately, they need to be resampled. In a traditional workflow, you would go in and you would resample these and save these out to a TIFF file and then go through your stacking process. Using Wherobots in the stack tile explode, all of that is really taken care of for you. So the near infrared, the band 8 is in the native 10-meter resolution. And when we use stack tile explode and specify this as our reference raster, SWIR 22 and SWIR 16 and any other band or any other raster layer that we wanted to stack would automatically be resampled and then co-located with that reference band. So we're doing a couple of processes. We're resampling and ensuring that all of those pixels line up together. Do a little bit of filtering here, so we ensure that just all of those images that intersect our full AOIs are available. We don't need anything around the edges. This returns about 6,600 individual image tiles over these areas for the entire year. The thermal anomaly index here is from Liu et al. In 2021. I'm not going to get into that, but I just wanted to comment that, here we apply all of our raster algebra functions. And so you can see kind of how we're doing this B12 minus B11 divided by B8A. As long as it matches these thresholds, that would be a positive thermal detection. So real quick, I want to switch over so that we can look at what those results are. Boom. Here's one of our sites here, and you can see that the output of that analysis is this flare detection mask. The kind of pixelated imagery that we see below it is the source imagery that we used, and we can see these flares in this area, very prominent, fully located and identified within here. We can see this one just below it to the south. Those same flares, even these smaller flares, appear to have good positive detections in them. So now that we've successfully detected flares using our algorithm, the next stage is to continuously monitor those over time. And when we see a drop from flare activity to no flare activity, and we'll get down here and look at those, boom, here, that gives us the indication that we need to start to try to detect methane. Is this the flare has been put out intentionally, or is the flare gone out and now we're having a leak? And so through the Wherobots platform, using our MCP servers, identifying the data, looking at what we've already done here, we generated kind of this shutdown event demarcation, right? And you can see that we go from these very large flare pixel counts down to these very low pixel counts, which gives us the signal that we need to look at the difference between those dates and do some basic methane detection. And so the reference methodology that we have here is, again, using those same Sentinel images. So we don't need to go back and reselect. We already have that information kind of cached within this workflow. And so then we can go through and kind of work through this algorithm of determining our reference reflectance, comparing that to the reflectance from the next date imagery, and kind of walking through and determining if we do have significant methane in there. And now when I ran this analysis, this again generates those same possible methane masks. Looking at all of the dates here, while we did identify these dropouts, like we weren't able to actually detect any methane from the field there. But there's a lot of other ways that you can do this. I think that this serves as like an early warning signal for you guys to plug in like higher resolution imagery. Using raster flow and using some of our other products, you can actually deploy machine learning models that are more successful and more accurate. With these, we can actually take these sites, take the same window identification, if we go back and look at our chart here, and trigger additional jobs. And so if we needed to download hyperspectral imagery or task acquisition from Planet or Worldview to be able to collect high resolution imagery over these areas that is has a better spectral signature for detecting methane, like this can trigger that type of workflow too. I want to check and see if we had any questions or any comments. There's a chat that we should be able to. Ben, do you see any questions or any comments before we kind of jump into the MCP server part of this?
Let me check the questions section. I don't see anything in the nope, go ahead, keep going.
Perfect. So, in a perfect world, right, the analysts are working and they're iterating to determine these processes. They land on a process like this that they're comfortable with, that is acceptable to their leadership and to the rest of the industry. And now, they want to convert this into a process that can be done automatically, that can be done on a schedule or run with a click of a button without necessarily having to run the notebook and go into those types of infrastructure pieces and workflows that might be, time consuming to just open this notebook and run the whole thing. Like, we can just put this on a job. And so we're going to use Claude, and like I said, this is tied directly to our MCP server, which has an understanding of all of our internal design patterns, all of our Python SDKs for running automation. We have CLI tools, as well as Airflow providers to kind of orchestrate, regularly scheduled jobs. And so I'm just going to ask Claude here to convert this use case notebook, the Methane MBMP screening, to a Wherobots job. And I run Airflow, but I really prefer Python, like, just in general. And so I'm going to pretend that, I don't have access to Airflow, and I'm going to ask it to orchestrate a job. I want the job to use the Wherobots Python SDK. I need the job script and so the way that it works within Wherobots, let me jump over to our workload history over here. Is there's really two parts to this. There's the individual script that gets run, and so that is the shortened version of the notebook that we had. So removing all of those print statements, removing all of the shows and the counts, all of this unnecessary stuff when you're automating a process, but are very critical for debugging and looking at the results when you're in this kind of interactive analytic workflow. The other part of this is the orchestration side. And so that script has to be moved over to the platform so it can actually be executed. It has to be, authorized and authenticated in all of the pieces that go into running that job, the runtime, the timeout settings, the size of the environment you want it to run. All of those different characteristics need to be sent as parameters to the job. And so we're really doing kind of two things here. It's working on both the job script, which is the conversion of the notebook, as well as the orchestration side. It's actually referencing some additional scripts that we've already had here. So I've had a benchmark running for the actual flare detection itself over vast areas, not just the 6 or 10 sites that we have here. And then the benchmarking here, which kind of iteratively runs through that at different scales. And so we're going to give it just a second. It's kind of noodle through here. It's funny that's using the word noodle. And it's going to generate these scripts for us while the foundation model kind of does its thing. And before we jump into that, we do have time for some questions. If anybody has any questions or comments or concerns about the functionality or what else we can do within Wherobots.
Hey, Daniel, maybe one that I know you kind of covered on at briefly while you were introducing the notebook, but you know, we had this poll question, but like you can, three patterns that I use are MCP server for. One is like just figuring out what data that I've got that are useful for a particular analysis, right? Like oftentimes one of the challenges when you're dealing with spatial data and it's just like locating the various different data types that you might be able to use, connecting those in, like that whole set of things. Then there's okay, now I want to build the analysis. Like, what are the best practices out there to go build this analysis? And then how should I apply them to the data that I have? So anyway, I just would love for your just like input on how you think about those things when you're using these modern AI coding tools and collaborate in connection with Wherobots.
Definitely. The database introspection is like a critical first step, especially when you're onboarding new people to your organization, right? Like that is not necessarily an easy task. And frequently you have tons and tons and tons of data. It's not always thoroughly documented. So being able to use, yes, we'll go ahead. Using the MCP server to kind of shortcut all of the reading of the data dictionaries, the combing through the schemas, combing through multiple databases, multiple S3 buckets, kind of just, I hate to use the term grokking, but like, using the LLM and using Claude to just, in the MCP server, to introspect the data, summarize what's there, and then give you insights into what data is available, what it could be used for, and even, chasing the metadata that's available. We expose all of the table properties to our MCP server. So when you're importing, when you're using the MCP server to kind of investigate your data, it can actually read all of the table properties that have been put in and then go and search the rest of the wider web to give more context to those. And like the gateway to that is through the MCP server. When it comes to the development of the notebook, like I said, like I'm not an SME in oil and gas, but I know enough about it, and I know enough about the environmental constraints that we had talked about in the monitoring to be able to feed it enough context with the data and what I'm trying to accomplish to generate notebooks like this. It's really become an integrated part of my workflow. And then on the backside, like you were saying, the automation of that, once I have, discovered the data that we have in-house that's available for my analysis, possibly imported and generated more data that would be needed, using and iterating with the MCP server to land on an analysis using Wherobots best practices, and then using those results with the foundation models, backed by the MCP server and the spatial skills and the kind of working skills that we've developed in our best practices to roll that right into a job automation is really kind of how I go through my workday when working on demos, when working on webinars, working directly with customers in our customer projects. Yeah, it's really accelerated like my ability to deliver internally and externally pretty much across the board.
Awesome. Kirk Bradley or sorry, Kirk, I didn't mean to say your last name. Had a question or comment. If some part of the script fails, does it self-recover and continue, or do I do that by hand? How do you solve that?
That's a great question. So part of the skills and part of the MCP server, whenever, like, if I were to take this job and say, cool, you've written my job. If we look here, we can see my methane detection screening job here. And you can see my orchestration, methane, MBP screening here. Part of the Python SDK, if we scroll down here, boom, 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 we can see our timeouts, job submit, right here, wait for completion. So when you use the MCP server in conjunction with the foundation models to then like run this job, the background processes will wait and look and listen to the logs being generated. And when it fails, you can, if you give it the the autonomy to read the logs and check and kind of self-heal, it does an amazing job of being able to parse our logs, use our skills, use basic understanding of Spark and the environment to then heal that job and then resubmit it. Like this is a pattern that I've been through multiple times where you get to a spot here and you'll have something like an endpoint isn't recognizable, right? And it surfaces that in the logs, goes through and comes back through. So the answer to your question is no, you don't need to do that by hand. The MCP server coupled with the frontier models are fully capable of running the orchestration, monitoring the results, recovering from errors, updating the logs, and then resubmitting them until completion or certain thresholds are met for success. It's a great question, Kurt. Yeah, I think that, on the end of this took a couple of minutes to kind of get through, but in the end, like we can take a look at our job. All of these have been parameterized up front. So like, what is our cloud covered? If you remember, in our screening notebook here, it's done a great job. And so these are the things that are built into the skill that we've kind of set up. You can see here, cloud cover is hard coded as 10%. But the skills and the MCP server have informed Claude that, hey, when you see certain conditions like this, things that are apparently parameters, and we fed it all of our documentation so it understands what can be parameterized, it does the nice work of kind of setting those up in the very beginning of our script so that they can be easily edited or easily modified. You actually get overrides for these in here too. Here's the MBP threshold that is referenced at the top. Few of these other ones here. So like it does an amazing job of converting your analytic notebooks or your analytic scripts, if you have just kind of one-off scripts that write locally, into running Wherobots jobs, as well as the orchestration part, where, like, Kirk, back to your reference, like it will wait for completion if you want it to, and then be able to write back and kind of tell you what's happened, so on and so forth. I'm going to pause here for a few minutes and see if we have any additional questions or the other content that we want to review. I think a couple of the things that I'd like to note in here is, the analysis that goes into here is using Sentinel-2 imagery, but there's no restriction on the platforms or the sensors or the numbers of bands. We've worked with hyperspectral imagery, drone imagery down to, centimeter resolution, weather data, weather pattern, wind, all of that type of data can be integrated into the platform to build much larger comprehensive models for whatever your process is, if that's flare detection, methane detection, CO2 detection. All of those sensors and payloads and platforms are fully supported within the product, and able to run these types of analytics at scale, whether that's a few hundred sites, a few thousand sites, global scale monitoring. All of that is within reach with the Wherobots platform. All right. I think we got about 7 or 10 minutes left on our webinar. Phil, Ben, do you guys have anything else you'd like to add? I'm going to stop sharing now. We can pause for a few questions.
Yeah, just one more thing I want to cover. Switch over back to the slides here for a second. But yeah, Daniel, maybe just want to restate the overall scale and performance we're seeing just for the sites you showed here with this slide.
Yeah, perfect. And so I think like the headline here is 6 LNG sites and entire year's worth of imagery analyzed for $5 in 4 minutes, right? This would be like a very retrospective, but you can automate this to go and check every single site every single day, excuse me, looking for the most recent Sentinel overpass and doing the same workflow. This is extremely like plug and playable in terms of what are the sites. As you saw at the beginning, it's just like a GeoJSON data set here. You could drop in a new GeoJSON data set every single day, have it process the same GeoJSON data set every day for the latest imagery. And we kind of just go through here, like, again, that Liu et al. Paper from a few years ago, kind of lauding that tri-band thermal anomaly. We found that it works really, really well. For these, there's a spot where it does start to kind of drop out, but I think that's noted in the article, when you have extremely high temperatures. And you can actually see a little bit of that drop out in the center of one of these clusters here. But all of the expression of that is band math, right? Colloquial term map algebra. And all of those functions are fully expressible within the platform. So if you're doing advanced algebraic equation to calculate anything, frankly, or simple band math and simple indexes, like this one here based on thresholds, all of that is available within the platform at scale.
Cool. All right, thanks, Daniel. So just one more thing. Let's take up another poll question. Given the type of pipelines that Daniel was just discussing, I want to understand from you guys, how far along are you in operationalizing this type of workflow and this methane detection?
All right, we got a few different responses. Pretty much everybody is saying that they're investigating options. So cool. Good. Well, we're here to help.
Okay. Well, that's a good segue to our next slide, our final slide. If you're investigating options and you're looking for a partner to work with on this, we'd love to talk to you. We have a new initiative we call Wherobots Labs. It's all about making Wherobots more useful for enterprises for specific use cases. And it's a collaborative project where a lot of these examples that we're providing, whether it's connectors and adapters, things like QGIS and DBT, or specific workflows and pipelines and notebooks that we're providing for specific industry examples, or a set of MCP server skills that we've battle tested that work well for using modern LMs. We're providing a bunch of these to help people understand what they can do with Wherobots and make it easier for them to integrate it into their environment. But we're also looking for customers and partners to work with us on this, or even make contributions themselves. And one of the specific initiatives in this Wherobots Lab program that we're looking at is methane monitoring. So how can we work together with Wherobots and industry partners to help solve this problem at scale? So we're seeking collaboration from anyone who's interested, looking at your expertise in the ideal methane detection methods, our expertise in running these types of pipelines at that global scale, so we can ultimately work together as an industry and as humanity and help solve this problem. So yeah, let us know, reach out if you're interested. And yeah, as one final poll, just to see who's up for that, let us know if you're interested, and we'll reach out and set up that collaboration. All right, while people are filling that out, just show the final slide. That's basically concludes the webinar for today. But feel free to reach out to myself, Daniel directly, or fill out our contact form if you'd like more information. We'll be following up directly with anyone who's filled out that last survey as well. But yeah, definitely time for questions if there are any questions from the field here while we're still around. All right, Ben, you see any questions on your end?
No, I don't have any additional ones that are coming through. Any final thoughts from you guys? Advice, suggestions, ideas? Daniel or Phil?
I would be really interested in working if there is a methane plume, like of known location and known time with imagery. I would love to collaborate with anybody on the call. We kind of run that algorithm and their data through this platform to see how well the methane detection works for like a known site. I think that's one of the things I really was hoping to find. You don't want to find a methane plume, but you also want to find a methane plume when you're kind of doing these projects. And I would really be fascinated to work with somebody who has either the higher resolution data or an example that they would like to see if we can do that. You see how well that their algorithm works and performs within the platform at scale. So that would be the only thing that I would like.
Cool. The only thing I would add is just if you're not in oil and gas, but you see some relevance to the types of workloads we're doing here for your specific industry, reach out to. We're happy to look at other areas, other use cases where we can show off our value on running these pipelines at global scale, and happy to strike up that collaboration with you if you have a specific use case in mind. All right. No further questions. I think we'll sign off for today. Thanks everyone for tuning in, and stay tuned for other additional webinars coming up with similar subject matter. Thanks again.